principles. How do we differentiate sine 2x from first principles? So we've seen that from first principle, the derivative of a curve is given by limit as the small change in x tends to 0 of f of x plus the change in x minus f of x over the small change in x. So that is how to determine the derivative of a curve. So when you are told to differentiate, it means they want you to determine the derivative of that given function sine 2x. Are we together? You are told to determine the derivative of that function sine 2x. So the first thing you know what is inside here before you apply the limits is the gradient, isn't it? So how do you determine the gradient? So the first thing you say, when you are sketching any curve, the curve must be a function, isn't it? So if you are given sine 2x, meaning this is a function of x, isn't it? So you say, if y is the function of x for this given curve, then it means that y is equal to sine 2x. So this is the curve you are going to, this is the function you are going to sketch on the graph, isn't it? So they want you to determine the derivative of this function. So if you don't do this from first principle, it is just differentiating y with respect to x. You get dy over dx to be 2 cos 2x. That should be the answers we are going to see later in the course. But now, how do we do it from first principles? Are you seeing that? How do we do it from first principles? Now the first thing you need to do is to determine this gradient, because what is inside before you take the limits to get the derivative, what is inside here is the gradient. So you have to determine the gradient, isn't it? How do you determine the gradient? You must have 2 points on the curve, isn't it? That is when you will be able to determine the gradient. So you must have 2 points, x1, y1, and another point, x2, y2, isn't it? Are you seeing that? Then you start listing. What is x1? X1 is, for you to determine the gradient, 1 point is known and 1 point is unknown, isn't it? 1 point is known and 1 point is unknown. So the unknown point is always the arbitrary point, a point which can lie anywhere along the curve, isn't it? So the arbitrary point, if you let x1, y1 to be the arbitrary point, xy. Because if you are in the Cartesian coordinate system, the xy plane, it means xy is the arbitrary point. It is a point which can lie anywhere, isn't it? X can be 0, y can be 0, so that you have a point 0, 0. X can be 1, y can be negative 1, so you have a point negative 1, negative 1. So x is any point, arbitrary, isn't it? So you have one unknown point, and this x2, y2 is the known point, isn't it? Are we together? Are we together? So let us now start. We now want to start substituting. We get all the values. So x1 we found is equals to x, isn't it? Are we together? Then what is y1? Somebody, what is y1? You found x1 is x. What is y1? x1 is x. What is y1? Remember, y is a function of sine 2x, meaning if this is y1, this is x1. This is the criteria. So it means y1 is the same as sine 2x1. Then you substitute the value of x1 because everything must be in terms of x. Are you seeing that? Because you can see this is a function of x change in x, meaning everything here, x1, y1, x2, y2, everything must be in terms of x alone. Are you seeing that? Are we together? Are we together? So it means x1 is x. Where there is x1, you put the value of x1, which is x. So it means y1 is sine 2x. So it means the function which you are always given is always y1. Are you seeing that? The function you are always given is always y1. Then you now move. What is x2? x2, for you to reach x2, see you are moving from x1 to x2, meaning there's an interval between, isn't it? And that interval is the small change, isn't it? Are you seeing that? So it means if you had, this is your curve, if this is x1 and this is x2, and there's a small change in x between them. So it means x1 plus this small change in x gives you x2, isn't it? So it means x2 is what? x2 is x1 plus the small change in x, isn't it? But x1 you know is x, so it means x2 is just x plus small change. Are we together? So all these three will never change in any function. x1 will remain x, y1 will remain the function itself, x2 of course will be x plus the change in x. Are you seeing that? In any function, they will always be like that. Are we together? Now the case now goes back to y2 is what we are left with. So what is y2? y2 is, we said y is the function, meaning if this is y2, then that is x. Are you seeing that? Because y is a function of x. If it is y, it is x. If it is y1, it is x1. If it is y2, it is x. It is that function of the curve you are using to get all of them, isn't it? So it means y2 is sine 2x, x2, isn't it? Are we together? Are we together? So what is x2? Good. So x2, where there is x2, you substitute the value of x2, isn't it? So x2 is the same as, we have sine 2, where there is x2, put the value of x2, which you said is x plus change in x, isn't it? Then after doing that, what do? So you simplify. So if you simplify that, you get sine in bracket 2 times x is 2x plus 2 times change in x is 2 change in x. So you found x1, y1, x2, y2, meaning you can determine the gradient because you found all the 2 points, isn't it? Are you together? So what is the gradient? So the gradient is what is inside. It is the change in y, which we've spelled out how this come about to be the change in y, and this is change in x. So change in x is x2 minus x1. So you can see x plus change in x minus x will always remain change in x. Are you seeing that? Are we together? Are we together? Will always remain change in x. Then now, you now come and write that. So we now have the 4 points here. So the first point for us now to get the derivative dy over dx, we are simply taking the limit as change in x tend to 0 of the gradient. So can you now put the gradient inside because you have the values which gives you the gradient, isn't it? Are we together? Are we together? You put the gradient inside. Gradient is change in y over change in x. So what is change in y? Change in y is y2 minus y1, isn't it? Meaning change in y is sine 2x plus 2 change in x minus y1, which is sine 2x. That is change in y, y2 minus y1, isn't it? Are we together? Then you move to the denominator. Change in x is x2 minus x1, which will remain with change in x, isn't it? Now if you look at this problem, what happens? When you try to substitute this change in x as 10 to 0, you see there's 0 in the denominator. You see that? There's 0 in the denominator. So in that, this is a very small change. It is a case of indeterminate form. So if it is a case of indeterminate form, you cannot eliminate the limit by substituting change in x to be 0 in this problem. You must come up with a way to ensure that you are able to solve this given problem when there is no subtraction between them, because you can see it will result in determinate form in that the denominator will go to 0. So you cannot see the solution of that derivative. You cannot find that derivative, isn't it? Are you seeing that? Are we together? Because if you substitute this, first of all, if you look at denominator alone, it will be 0. So anything over 0, you will never get the answer, isn't it? So you must now go back and recall trigonometry. You can recall factor identities and the factor formulas and the product identities, how they were working, so that you are able to transform this one from 2 terms to 1 term. Because from limit theory, you can see this is same. So if it is involving same, in limit theory, what did we see? We saw that when you have limit as x tends to 0 of sine x over x was indeterminate form, isn't it? And this indeterminate form, when we applied the L'Hopital's rule, we found it to be 1. So that means that when you take this limit inside, you'll have limit of this and limit of that over limit of this, isn't it? But now when we use factor formulas and product identities, we will be able to transform this subtraction back to multiplication so that when you have a minus b over c, this is a over c minus b over c, isn't it? But now when you have a dot b over c, this is simply either a over c times b or a times b over c, meaning c is denominator of only one thing. Are you seeing? So it means when we transform this subtraction sign to multiplication, this change in x will be over either one thing if they are a product of two, isn't it? And when it is over one thing, we are able to find a case of this indeterminate form where we use a L'Hopital's rule to get this. So you see, that is why we're saying this limit is very important. So once we are able to transform, so if we change in x tends to 0, meaning this one is changing x, meaning you will get such a case, isn't it? Are we together? If you transform it to multiplication, this change in x in denominator will be over either one of them, but not both of them, like in this case, isn't it? Is that okay? So we now go back to the product identities and we see which function was giving you, was resulting. Here we have sine minus sine, meaning we are dealing with, we have sine. This angle is different from this angle because this is 2x plus 2 change in x. It's different from 2x, isn't it? Are you seeing that? So it means if this is a, this is b. So it is like we have sine a minus sine b. Are you seeing that? So we have the two, here we are dealing with sine. So we have to deal with the two cases of the sine, sum, and difference angle formula. So what did you add in the sine, sum, and difference angle formula? When you add sine a plus b, this was sine a cos b plus sine b cos a. Then when you add sine a minus b, this was sine a cos b minus sine b cos a, isn't it? But you remember, we want sine minus sine, meaning we subtract the two equations to get sine minus sine. Because you can see angle a plus b is this, a minus b is this, because they are different angles, isn't it? Are you seeing that? So for us to get sine minus sine, meaning we must subtract the two equations. Is that okay? So if you subtract the two equations, what do you get? Sine a plus b minus sine a minus b, you get sine a plus b minus sine a minus b. That is what you get, isn't it? Then if you go to the other side of the equation, what do you get? This minus this is 0. Then here, this minus this, you get 2 of them, isn't it? So that side we have 2 sine b cos a. Are you seeing that? Now, you now do the change of variable because you ensure this is one angle and this is one angle, isn't it? So how do you ensure? So you can say, let a plus b to be one thing. You can let a plus b to be theta and a minus b to be beta. So that you have sine theta minus sine beta. So the whole of this angle 2x plus 2 change in x is theta and 2x is beta. It is now one thing. Have you seen that? Are we together? Huh? Yes. So from here you now see sine theta minus sine beta, meaning you say theta to be a plus b and beta to be a minus b, isn't it? So what do you get here? When you add the two equations, what do you get? When you add the two, theta plus beta is equals to a because b plus negative b is 0, isn't it? When you subtract the two equations, what do you get? So from here you can see you can get the value because we want the value of b and a, isn't it? So what is the value of a? So you divide both sides by 2. So you found a is theta plus beta over 2. Then you go again. When you subtract the two equations, it is theta minus beta, isn't it? Theta minus beta is equals to b minus b is 2b, isn't it? So theta minus beta is equals to 2b. So that implies that b is what? You divide both sides by 2, isn't it? So you get b is theta minus beta over 2. So you go back and you do the substitution, meaning here we have sine theta minus sine beta is equals to 2 sine b. But what is b? B is theta minus beta over over 2, then sine A. What is A? Because everything must be in terms of theta and beta only, isn't it? Are we together? What is A? Theta plus beta over 2. A is theta plus beta over 2. So if you look at that, you now go back and say, what is your theta? You have sine theta. Meaning, what is your theta? This is sine theta minus sine beta, isn't it? Are you seeing that? This is sine theta minus sine beta. So what is theta? Theta is 2x plus 2 change in x, isn't it? And what is beta? Beta is 2x, isn't it? Are we together? So can you now do the substitution? So if you do the substitution, theta to be this and beta to be that, what do you get? If you do the substitution, theta to be 2x plus 2 change in x and beta to be 2x. So do the substitution back there. So we've dealt with this, we are done with this. We are going back to the problem. Here is where we are now. Here. Go back to the problem and do the substitution. So this is equals to limit as change in x tends to 0 of sine theta, isn't it? Minus sine beta. So what is sine theta minus sine beta? Meaning where you have this numerator, you put this, isn't it? Because sine theta minus sine beta is the same as this. Are we together? Are we together? So where we have sine theta minus sine beta, we put 2 sine theta minus beta over 2, isn't it? So give me that value. What is theta minus beta over 2? Theta minus beta. You remain with this minus this. See, 2x minus 2x is 0. So you remain with the 2 change in x. You remain with the 2 over 2, isn't it? So at the end, you remain with change in x, isn't it? Are we together? So this theta, this theta minus beta over 2, which we are substituting here, we found it is just change in x, isn't it? Then it is times cos theta plus beta over 2. Say are we together? Theta plus beta over. So can you add this plus this divide by 2? See, it is 4x plus 2 change in x, isn't it? So 4x plus 2 change in x divided by 2. So you remain with 2x plus change in x, isn't it? Because 2 goes here, remain with 2 change in x, isn't it? So you've now transformed subtraction into multiplication. Then the whole of that numerator is over denominator, which is changing x. So you see, we are now using trigonometry to transform it back in a manner that we are now able to put the denominator over one of them. Meaning this change in x is either over this or over this because of multiplication, isn't it? Are we together? Then you go back, we said that important limit we talked about. When you had the limit as x tends to 0 of sine x over x, meaning you must always put it over sine and sine with only one term. Are you see that? It must be over a sine function, isn't it? It must be over sine function. So can you put it over sine function? If you put it over sine function, what do you get? You get limit as change in x tends to 0 of this 2 is a constant, can be factorized outside, isn't it? Are we together? If you factorize this 2 outside, what do you remain with here? You remain with sine change in x over change in x, then times cos 2x plus change in x. So if you remember what we started with limit theory, what did we say? We said when you have limit as x tends to 0 of a dot b, this is simply limit of a as x tends to 0 times limit of, isn't it? See, this is what we said from limit theory. So it means this limit which is outside, it is for both this and this, isn't it? Do you recall that? So when you use the L'Hopital's rule, you found out that this limit is always, isn't it? Sine x over x, if change in x, if you put it to be x, it is like sine x over x, isn't it? If you let change in x to be y, it is sine y over y. And that limit we found from L'Hopital's rule to be 1, because this limit which is outside the bracket, it applies to this and this. Are you seeing that? Are we together? So what do we remain with? We now remain with the 2. Then we now, for us to get rid of the remaining limit, because this first limit we've already found to be 1, isn't it? Then the second limit is now what we eliminate by substituting 0 where there is change in x to get rid of the limit, isn't it? Are you seeing that? Are we together? So where there is change in x, if you put 0, what do you remain with? You remain with cos 2. If you put 0, yes, you remain with cos 2x. So what have we found in the end? 2 cos 2x to be the derivative of the function sin 2x. Are you seeing how it is simple? Very simple. So that is how we handle